Hey guys, welcome to part 3 of the 2012 level 2 waves, okay? So this will be probably the part you'll need for the upcoming grade waves topic test, okay? So question 3, waves. The following diagram shows parallel wave fronts approaching the shallow water. Waves travel slower in shallow water. Complete the diagram with labeled arrows showing the following. Direction of incident wave fronts, direction of travel of reflected wavefronts, and direction of travel of refracted transmitted wavefronts. Okay, so we have our we're gonna be drawing our so as you can see, the waves the horizontal, okay, and this means that if the horizontal is moving in a downwards position, okay, so it's going to be moving down towards the shallow water. Okay, so that's our for example, there's our ray of incident ray. Okay, so here's our incident ray. It's going to hit the shallow water, and if we're going to refract, then what will happen? Okay, because it slows down in the shallow water. Okay, I'm going to draw our normal line. Okay, our normal line is going to be no, it's not gonna be here. It's gonna be 90 degrees to a barrier. Okay, so it's gonna look something around here. Okay, so when the incident ray travels from deep water to shallow water, because deep water is less dense than shallow water, that means the ray will be bending towards the towards the normal. Okay, the ray bends towards the normal, and therefore it will look something like this. Okay, but the reflected waves. Okay, that will just be this will be, so this is our angle theta here. Okay, so when it rebounds back, this will also be angle theta, okay? So basically, okay, I don't have a protractor with me, so I'm going to estimate, okay? I'm going to estimate what it would look like. So we have our incident wavefront. This should, yeah, that looks about right. Yeah, that's here it's angle theta and angle theta, okay? So we have our rays drawn, okay, so we're going to say that this, so this one is the incident wavefront, okay, and this is our refracted, and this is our reflected. Okay. Let me just check. 3 correct rays. Diagram shows angle of incidence equals angle of reflection. Yeah. Angle of incidence is greater. Yeah. Okay. So basically, to get all 3 rays correct, okay, that will get you a merit grade. To get two rays correct, you're showing 2 correct rays. Okay. So any 2 correct rays will get you an achieved grade. Okay. Draw the refracted wavefronts for the same situation as given above, and draw the refracted wavefronts for the same situation as given below in the diagram below. Okay, so basically, we're gonna draw our what did I keep saying refracted? We're gonna draw our incident ray. Okay, so it's gonna hit this point. Okay, once again, we're gonna draw our normal line. So just give me a second. We're gonna draw our normal line. Okay, that's 90 degrees to a barrier, perpendicular to a barrier. So that will be somewhere, that will be here. Okay, I'm going to extend this. There's our normal line, okay? Our wave is going to be bending towards the normal, okay? Okay, so therefore, all of these waves here will be perpendicular to our refracted, will be perpendicular to our refracted ray, okay? So if we, okay, so so here comes the tricky part. We're going to be making it perpendicular to our refracted ray. So should look. Okay, this is a bit hard to draw, so I'm going to move this a little bit to make it a bit easier for me. So. bit more. Yes, this is the part where you kind of have to play around with your ruler to make it not too hard to draw out. So maybe a bit more. Yeah, that works. Okay, so that's our refracted wave fronts. Okay, so we're gonna do the same for the next one. So our refracted wave fronts. So should. Okay, so basically one way to check your answer is, as you can see, the wavelength should be smaller because we're moving from the we're moving from the less dense medium to the more dense medium. So therefore, our wavelength should decrease. Okay, because our wave slows down in the shallow water, therefore our wavelength should also decrease. As you can see in the diagram, our wavelength has been decreased. So therefore, we are on the right track. Okay, so we're just gonna draw our next ray here. Yeah. Just like, oh. Okay, so our next one, it doesn't have to be too perfect, but has to look good enough for the marker to not penalize you. So yeah. We have our it's getting a bit hard to draw. Yeah, I'm just gonna leave it there. I'm not gonna do the last one. I'm just gonna leave it here. Okay, so here's our refracted wave fronts. Okay, so diagram showing refracted wave fronts. So approximately in the correct direction. Okay, so yeah, this will get you this should get you a merit grade to get the correct wavefront in the correct direction. To get an achieved grade, you're looking at approximately in the correct direction or diagram showing reflected wavefronts. Okay, so achieve this any two of those points. Okay. Alright, so moving along. A boat is anchored in the harbor. Wait, just let me delete this. It's a pretty bad drawing, I must say. A boat is anchored behind a sea wall separating from the open sea. There is a gap between two sea walls as shown below. A sea wall is a structure that is built to protect the harbor from waves. Waves from the sea go towards the gap between the two sea walls. On the diagram below, show what happens to the waves once they go through the gap between the two sea walls. Include direction of the waves in your drawing. Describe and explain the effect on the waves it will have on the boat. Okay. Okay, so okay, so basically, okay, so basically, because as you can see, there's a gap size here and there's a wavelength here. As you can roughly see, the wavelength is greater than the gap size. Okay, so therefore there would be a high amount of diffraction. Will be a high amount of diffraction occurring. Okay. So if we were to draw this, okay, if we were to draw this, then it would be look something like this. So how about diffracted wavefronts would look like a semicircle. So therefore, okay, the wavelength should be the same. So it's too much. Yeah, it's pretty hard to draw on the device. So forgive me for this one. Okay, so it should look something. It's not very good drawing, but it should look something similar to that. Okay. So describe and explain the effect the waves will have on the boat. Okay. So basically, so we're gonna have our direction of travel. Okay, so it's gonna be going here. Sorry. Here. And Alright, so that's our diagram, okay? So therefore, okay, so we're gonna explain, okay? So we're gonna say when the waves when the waves move through the gap, they will diffract. They will diffract and bend in semicircles. Because the lambda is greater than the gap size. Lambda is greater than the gap size. A high amount of diffraction will occur. Therefore, there will be a high amount of diffraction that is occurring. Okay. So therefore, when the waves bend, it will hit the boat. It'll hit the boat, and what effect will that have? Okay, so when the water waves hit the boat, okay, the boat is gonna bob up and down. Okay, so imagine a duck. Okay, a duck is easy to imagine. Okay, let's say there's a wave coming, so it's just gonna go up, and it's gonna come back down. Actually, that's not a very good example. Actually, imagine a surf. Okay, so a surf is gonna be a wave coming. Okay, the wave's gonna come, and then the surf is gonna bob up, and then it's gonna come back down. Okay, so it's just gonna have a bobbing effect. Okay, effect will hit the boat, and therefore the boat will bob up and down in the water. Okay, so to get the excellence in this question, okay, you have a correct diagram showing the direction of the waves. So that's your diagram here showing the direction. That's 1 point, okay? The second point is the waves will diffract around the gap and the barrier. So you're mentioning that there's a diffraction in the gap, okay? So here that they will diffract, okay? So mentioning that the waves will diffract around the gap and the barrier. And you're saying that the boat will move up and down as the wave passes under it. So you're going to say that the boat will bob up and down in the water. Getting all 3 points will get you an excellence grade, okay? To get a merit grade, okay? To get a merit grade, you have the correct diagram, so that's a must-have. It's a correct diagram. Or you can have, and you have one of these, okay? So you say that the waves will diffract, or you can say that the boat will move up and down in the water. So diagram plus any will get you a merit grade. To get an achieved grade, you have your correct diagram, okay? So the correct diagram only will get you an achieved grade. Hey guys, welcome back to part D. Okay, so sorry, the last video got cut off, so I'm just gonna get straight back into it. Okay, the diagram below shows parallel wavefronts approaching two gaps. The wavelength of the waves is 4 meters. Okay, that's very important. The wavelength is 4 meters. A boat is anchored 3 meters from gap A and 5 meters from gap B. Describe and explain the effect of the waves on the motion of the boat, giving reasons. In your answer, state what happens to a wavefront as they go through the two gaps. Okay, so as you can see, A, okay, it travels 3 meters to get to a boat, and B travels 5 meters in order to get to a boat, okay? The difference, okay, so B has to travel 2 meters further, okay? And it's good to, note down that the wavelength of the wave is 4 meters, okay? So wavelength equals to 4 meters, and the difference, so 5 minus 3 equals to 2 meters. That's the path difference, okay? So 2 meters, that's the path difference, so B is 2 meters longer than A. So in order for a wave to travel from B to the boat, it needs to travel 2 meters longer than A. So that's technically what is the difference between the two paths, okay? Okay, so basically, because we have our 2 meters here, that's our path difference, and our wavelength is 4 meters, okay? Note that we have our 2 meters and 4 meters. Our path length is half our wavelength, okay? So therefore, there's a destructive interference. So remember back when they taught you when they said that there's when a destructive interference occurs when a wave trough meets with a wave crest. That's when the destructive destructive interference occurs. Okay. The distance from a wave trough to a wave crest is half a wavelength. Okay. So if I were to travel from a wave trough to a wave crest, the total distance there is half a wavelength. Okay. So because our path difference is half our wavelength, then we'll say that the path difference, okay, so it's a half of the wavelength, so therefore that the destructive interference will occur, and therefore the waves will cancel each other out. Okay, so these waves will destructively interfere, so whatever goes through A, they'll cancel out with B, and therefore nothing will be felt by the boat. Okay, so therefore we're gonna say that point B is 2 meters further than point A. Okay, our path difference is 2 meters. Our wavelength is 4 meters, and because our path difference is half of our wavelength, this means that destructive interference will occur. This means that the destructive interference will occur. Okay, so the waves will cancel each other out. Will cancel each other out, and therefore nothing will be felt by the boat. Okay, or the boat remains as is. Okay, so in order to get your excellence grade here, so you're gonna say that the gap B is 2 meters further away than A, so therefore the path difference is 2 meters. That's 1 point. Okay, and our second point, this means that our path difference is just half a wavelength. Okay, so our path difference is half of our wavelength. So this means that there's a destructive interference. That's point 2. Our point 3 is because there's a destructive interference, the waves will cancel each other out, and therefore there will be no waves, and therefore the boat will remain calm. That's point number 3. If you get all 3 of these points correct, okay, you'll get an excellence grade. In order to get your merit grade, okay, you're looking at 2 correct points will get you a merit grade. And to get it achieved, you're saying that the boat will remain calm due to destructive interference, or you can say that circular wavefronts are produced as the wave go through each gap. Okay, so either one of those to get you an achieved. But to get excellence, okay, you need to be linking the path difference to the wavelength. Okay, so the 2 meters is half of 4 meters, so therefore the wave crest is going to interfere with the wave trough, and because the wave crest is interfering with the wave trough, they'll cancel each other out, and therefore there's no waves, and therefore the boat remains calm. Okay, so linking and then therefore the boat remains calm, or boat remains still. Okay, linking all 3 of these points will get you the excellence grade. Okay. Okay, thank you for watching this walkthrough of the 2012 level 2 waves. Okay, hope you enjoyed the video, and I'll see you in the next one. Thank you. Bye.